In this video, we will be taking derivatives of trigonometric functions. Example 1 says, use the limit definition of a derivative and the fact that the limit as theta approaches 0 of sine of theta over theta equals 1 to find the derivative of y equals sine of x. Now, before we start this example, we're going to need to use some trigonometric identities. And so I'm going to go ahead and write those on the screen as a reminder to what those identities are that are going to help us in this example. All right, so here are those trig identities that we'll need later on, which are the sum formula for sine and the half angle formula for sine. Let's go ahead and we want to find our derivative function, and we're going to use the limit as h approaches 0 of y of x plus h minus y of x all over h. So then we have the limit as h approaches 0 of sine of x plus h minus sine of x all over h. Now this is where our first trig identity is going to come in. We need to use the sum formula because we need to expand out sine of x plus h. And if we're using this formula, we can rewrite this as follows. Alright, so all I've done is using the identity, I've expanded sine of x plus h into this highlighted thing here using the sum formula. Let's proceed. Now what I want to do is I am going to rewrite my numerator, and I'm going to bring negative sine of x to the front. So let's rewrite that. Alright, so I've just reordered my numerator so that negative sine of x is in the front. And the reason that I did that was because you'll notice that this term has a sine of x, and this term also has a sine of x. So from those first two terms, I'm going to go ahead and factor that from the numerator in those first two terms. So let's see what that looks like. This is going to give us the limit as h approaches 0 of, I'm going to factor out negative sine of x, and then that will leave us with 1 minus cosine of h, and then we still have that other term there, cosine of x, sine of h, and this is all over h. Now what we can do is, because I have a sum right here, using the limit laws that we've learned, I can break this up into two different limits. The other thing that I want to point out is we factored out this negative sine of x, and our limit is for h approaching 0, which means that negative sine of x can be factored outside of our limit because it does not contain the variable h. And we can think about it like a constant in the eyes of the limit, because the limit has its variable being h. Alright, so I'm splitting this up into two different limits, and another thing that we want to point out is in the second limit, cosine of x also is a constant in the eyes of the limit because that does not contain an h. So I'm going to factor out cosine of x outside of my limit, and then we're going to have times the limit as h approaches 0 of sine of h all over h. Now, hopefully you can see some stuff that will end up simplifying. First off, we were given earlier that we know the limit as theta approaches 0 of sine of theta over theta is equal to 1, and that's essentially what we have right here in this limit, except instead of theta we have the variable h, but that makes no difference, and it turns out that that highlighted quantity is equal to 1. At this time, I also want to use the half angle formula. The way that we're going to do that is I'm going to take my half angle formula and I'm going to square both sides of that. If I do that, we end up getting from this identity that sine squared theta over 2 is equal to, I'm going to square that whole radical expression, and that would give me 1 minus cosine of theta over 2. And my goal in this equation is to solve for 1 minus cosine of theta. And if I isolate that, I can I can multiply both sides of that identity by 2, and so now we can see that 1 minus cosine of theta is equal to 2 times sine squared theta over 2. And the whole reason that I want to use that is, notice that I have 1 minus cosine of theta here, and here I have 1 minus cosine of h, so I would like to replace that with 2 times sine squared h over 2. So let's do some substitutions here. So we're going to have negative sine of x times the limit as h approaches 0, and this violet highlighted thing, I'm going to replace that, like I just said, with 2 times sine squared h over 2 all over h. And then plus cosine of x, and then this whole thing is equal to 1, so I have times 1 here. Okay, so we're almost to the finish line. Now I'm going to do something where I don't want this 2 right here in this numerator, because remember, in order for us to use the limit as h approaches 0 of sine of h over h, we need the thing inside of the sine and the denominator to be the same. So it turns out that multiplying something by 2 is the same thing as dividing by 1/2. So if I divide by 1/2, I end up getting this. And this is in a form that is more friendly, because now what we can do is we can break this up. Sine squared I could break up into sine of h over 2 times sine of h over 2. So let me erase this. And I'm going to have sine of h over 2, and then I can multiply this by sine of h over 2 like that. And I'll go ahead and write back in that cosine that we had earlier. And now what I can do is I can split this up. So we have negative sine of x times, I know that this limit right here that I just wrote out, that is equal to 1 based off the given information. And then I can also apply the limit as h approaches 0 to this. So all right, at this stage, sine of h over 2, I have the ability to use direct substitution on that. So if we do that, we'd have negative sine of x times, if I plug in h equals 0, I'd get sine of 0, which is equal to 0. And then finally, negative sine times 0 is 0, so all we are left with is cosine of x. And we've actually seen this in a previous lecture video when we were looking at the graphs of derivatives. So if you remember, we were given the graph of the sine function and we were sketching its derivative graph, and we saw or noticed that it was the cosine graph in terms of the derivative. So I just wanted to reiterate, we had y equals sine of x, and we found that the derivative was y prime equals cosine of x, which is really neat, and that's kind of the derivation of this derivative. So I'm just going to go ahead and box our final answer here. In this example, we have shown that taking the derivative of sine gives us cosine. We can do a similar proof for taking the derivative of cosine. So in general, the derivative of sine of x is equal to cosine of x, and the derivative of cosine of x is equal to negative sine of x. This is going to come in handy. Example 2 says find the 27th derivative of f of theta equals cosine of theta. So let's go through some steps here. Hopefully we don't have to do this 27 times, but let's see what happens. I know from that purple box just a moment ago that the first derivative of cosine of theta is equal to negative sine of theta. So now I'd like to find the second derivative. And that means that we have to take the derivative with respect to theta of negative sine of theta. Now, negative 1 is a constant, so we remember we learned that theorem that allows us to take a constant outside of our derivative, and now we just need to take the derivative of sine, and that gives us negative cosine of theta. Now we want to take the third derivative. So now we have to take the derivative of negative cosine of theta. And I can pull out the negative sign. So now we are taking the derivative with respect to theta of cosine of theta, which would be negative sine of theta, which would be sine of theta. And now I'm taking the fourth derivative. And the derivative of sine of theta, that is just cosine of theta. Oh wait, that's the function that we started with. Notice that. So if I were to take the fifth derivative, the derivative of cosine of theta, we've already found that in the first derivative, so we get negative sine of theta. And you'll see what happens is we just get a pattern here, because if I take the derivative of negative sine of theta, we've already done that in the second derivative. So we get negative cosine of theta. And then the seventh derivative, we get sine of theta. And then the eighth derivative, we get cosine of theta again. So are we able to use some kind of pattern to see what the 27th derivative would be? Go ahead and pause the video and see if you can figure out what the pattern is. We'll go over that in just a second. It kind of seems like it goes in kind of groups of 4. What do I mean by that? If you look at the fourth derivative, that's equal to cosine of theta. If you look at the eighth derivative, that's also equal to cosine of theta. So if I were looking at patterns, it appears that multiples of 4 in terms of the derivative is what is giving us cosine of theta. So my guess would be that the 12th derivative would be equal to the 16th derivative, which would equal the 20th derivative, which would equal the 24th derivative, which would equal the 28th derivative. And all those are multiples of 4, so we have cosine of theta. Now the issue is that 27 is not a multiple of 4, so in this pattern, I'm gonna go back 1. And so my guess would be that the 27th derivative of this function would be the one before cosine of theta, which in this pattern was sine of theta. So there is our answer for example 2. Now, I just want to make a quick note. If maybe you're majoring in computer science, this would come up, and same thing with math. This example uses something called the idea of modular arithmetic. And modular arithmetic is really just concerned with the remainder after you divide by something. So in this example, if I were to take the number 27, and if I were to divide it by 4, since that's when our derivatives started repeating, let's see, 4 times 6 is 24, and I'm left with 3. So my remainder here is 3, and you'll see that the pattern is if I have something with remainder 1, in this scenario we have negative sine of theta. If I have something remainder 2 after dividing by 4, I have negative cosine of theta. If I have something with remainder 3, then we get sine, sine of theta. And then finally, if something is remainder 0, because that means it's a multiple of 4, we have cosine of theta. So that's just some interesting facts and utilizing this other topic called modular arithmetic. Example 3 says, use rules that we have learned and trigonometric identities to find the following derivatives involving trig functions. Part A says, take the derivative with respect to y of tangent of y. Now, in order for us to be able to do this, we want to rewrite tangent using one of our trig identities, and we know that tangent is equivalent to sine over cosine. Now, we did this because we know the derivatives of the sine and the cosine functions, but notice that this is a quotient, and so we're going to need to use the quotient rule in order to do this. So I'm going to write this out. It's the bottom function times the derivative of the top function minus the top function times the derivative of the bottom function all over the bottom function squared. All right, let's see if we can clean that up. So I have cosine of y. The derivative of sine is cosine from above. We saw that in that purple box and we derived it earlier. Then we have minus sine of y. And then the derivative of cosine of y is negative sine of y over cosine squared y. All right, let's see what we can do with this. We have cosine squared y minus, if I multiply those two negatives, that's going to become plus sine squared y over cosine squared y. If you thought that the numerator looked familiar, you would be correct in that we can rewrite that using the Pythagorean identity. So from here, our numerator is equal to 1, and then we have cosine squared y in the denominator, and I'd like my answer here to not be a fraction, and so we can use one of the reciprocal identities that we learn in trigonometry, and we could rewrite this as secant squared y. So it turns out that the derivative of the tangent function is secant squared y. All right, in part B, we would like to take the derivative with respect to our variable alpha of secant of alpha. And again, we're going to use a trig identity because I don't know what the derivative of secant is, but I do know what the derivative of cosine is, and so once again using our reciprocal identity, I could rewrite this as 1 over cosine. Now if I want to take the derivative of this thing, I'm going to need to use quotient rule again because I have 1 divided by some other function. So let's go ahead and use quotient rule. I have the bottom function times the derivative of the top function minus the top function times the derivative of the bottom function over the bottom function squared. Now, the derivative of a constant here is equal to 0, so I have cosine times 0, which is just going to be 0, so I have 0 minus, and then the derivative of cosine is negative sine over cosine squared alpha. And my numerator, 0 minus negative sine, that will become sine of alpha over cosine squared alpha. And typically when we're talking about the derivative of secant, we don't leave it in this form. So I'm going to use some more identities, and first off I'm going to split this up into the product of two fractions. So I'm going to write this as sine of theta over cosine of theta times 1 over cosine of theta, or excuse me, alpha, not theta. And let's rewrite both of these things using trigonometric identities. I know that sine over cosine is equivalent to tangent, and I know that 1 over cosine is equivalent to secant. And multiplication is commutative, so you could either write it in that order, or I think it might be a little bit more common, commonly seen as secant times tangent. So either of these work as our derivative function. Let me just box one of them. Okay, so there's our answer for part B. Oh, hey, look at that. Here are the derivatives of the 6 trig functions. And one thing that I learned when I was taking Calculus 1 is that when you take the derivative of any of the trig functions that start with the letter c, its derivative is going to have a negative outside or in the front. So what do I mean by that? Well, if I am taking the derivative of cosecant starts with a c, and so you'll notice that it has a negative out in the front. If I take the derivative of cosine, that starts with a c, it has a negative out in the front. And then lastly, cotangent also has a negative out in the front. You will need to memorize these 6 derivatives. They're going to come up again and again, and so you want to make sure that you have these 6 formulas memorized. So there they are again. If you'd like to take a screenshot or whatever, just make sure that you have these things memorized. All right, let's move on. All right, in example 4, we want to find the following derivatives. So part A, we have the derivative with respect to theta of the square root of theta times tangent of theta. And you'll notice that I have 2 different functions that are being multiplied. I can call this one f and this one g. So in order to take this derivative, I'm going to need to use the product rule. And remember that this is the same thing as theta to the 1/2 power. I'm writing it like that so that it's easier to use the power rule on. Okay, so I have the derivative with respect to theta of theta to the 1/2 power times tangent of theta. So we have the first function times the derivative of the second function, which we just found to be secant squared, plus the second function times the derivative of the first. I'm going to need to use power rule on that. And then that's about it. We can clean that up if we'd like, or we can kind of just leave that as is. I'm okay either way, whether you simplify this or not. All right, so there is our final answer for part A. All right, for part B, we're taking the derivative with respect to x of the cubed root of x plus 3 times e to the x all over cosecant x. And once again, to make my life easier, I'm going to rewrite this as x to the 1/3 power so that we can use the power rule on that when we're taking the derivative. But notice that we have a quotient, so we're going to need to end up using the quotient rule. So I have the bottom function times the derivative of the top. I'm going to need to use the power rule. 1/3 minus 1 is negative 2/3. And then plus the derivative of the natural exponential function is just itself, so I have plus 3 times e to the power of x. So we did bottom times the derivative of the top minus the top function times the derivative of the bottom function. So I told you to memorize this. If you didn't, go back and look at that purple table from above. And we have negative cosecant x times cotangent x. And then this is all over the bottom function squared. So that's going to be cosecant squared x. Again, I'm okay with you leaving your answer like this. One thing that I'm noticing very quickly, if I wanted to, I could factor out a cosecant out of the numerator because I have a cosecant in this term and a cosecant in that term, and that would allow me to divide that with one of the cosecants in the denominator. So I have 1/3 x to the negative 2/3 power plus 3 times e to the x minus x to the 1/3 power plus 3e to the x times negative cotangent of x, because I'm factoring out one of the cosecants, and then that would leave me with a single cosecant in the denominator. So here is our final answer For part B, of course, you could go about cleaning this up a little bit more. I'm just going to go ahead and leave my answer like this. All right, for part C, hold on because it's going to be a bumpy ride. We have to take the derivative of x times e to the x times cosecant x. And if you notice here, this is the product of three different functions. And so what we're kind of going to do is I'm going to think about this thing as my first function, x times e to the x, and then I'll think about cosecant as my second function, but I'm going to end up needing a good amount of product rule. So we have the first function times the derivative of the second function, which we did earlier. That was negative cosecant x times cotangent x, plus the second function times the derivative of the first function, and that I'm going to need to use product rule again. So if I'm taking the derivative of x times e to the x, I can think about this as my first function and this thing as my second function. So I have first times the derivative of the second plus the second times the derivative of the first. And there we go. Again, if you'd like, you can simplify this. I'm just going to leave my answer like that. And that concludes example 4. It turns out that there is a quicker way to apply the product rule when we have more than two products. Let's try putting this formula to use. So if you see here, we have the derivative of some function f times g times h, and then we can have three sums where we take the derivative of f and then multiply by the regular g and h function, and so on and so forth. So let's see if we can apply that to example 5, where we're taking the derivative of that same function again. So in this case, our f function would be x, our g function would be e to the power of x, and then h of x would equal cosecant of x. And so the derivative here is equal to, we would take the derivative of the first function, so 1 times e to the x times cosecant x, plus x times e to the x, since that's the derivative of the middle function, and then times cosecant x, plus x times e to the x, and then we can multiply this by the derivative of cosecant, which is negative cosecant x cotangent x. And it turns out that this is the same answer that we got above if we just do some algebraic simplification. Go ahead and simplify this to see that you would get the same answer that we got in the previous example. Example 6 says find the derivative of f of x, which is equal to 2x cubed times e to the x times sine of x times tangent of x. Now we have the product of 4 functions. One thing that will make our life a little bit easier, though, is I can factor out the 2, since that's a constant, and then I can take the derivative of the remaining functions, which is x cubed times e to the x times sine of x times tangent of x, and we would apply that same formula that we had on the previous page. Now we just have 4 functions, so this is equal to, I can leave the 2 factored out, and then I would take the derivative of the first function, then multiply by the other 3 functions' original forms, then plus I would keep the first function the same, multiply by the derivative of the second function, but that's still e to the x. Plus, now I keep the first and the second function the same. Now I'd want to multiply by the derivative of the third function, sine, which is cosine of x, plus, now we keep the first 3 functions the same, and then just multiply by the derivative of the last one, which is secant squared x. And there we have our derivative of this long function, which has an even longer derivative. But here's our final answer. And that concludes this video on derivatives of trig functions. Thanks for watching.